For a long time, we thought of the moon as a dead world, a quiet, dusty rock that just hangs out in our sky. It did its job, pulling on our tides, and that was it. Scientists believed it cooled down billions of years ago. It was a fossil, a perfect snapshot of the early solar system, unchanging and still. But we were wrong. I'm here to tell you that NASA has found something incredible. The moon is not as quiet as we thought. Deep inside, it is alive and moving. It's a secret that has been hiding in plain sight, waiting for us to develop the tools to finally see it. This changes everything we thought we knew about our closest neighbor. Imagine a world that is supposed to be solid, suddenly showing signs of life. That's what we're seeing. New data is telling us that the moon's interior is still hot. It's churning and shifting. This activity is causing the surface to flex and move in subtle ways. For scientists, this is a huge surprise. Think about it, a small world like the moon should have lost all its internal heat ages ago. It doesn't have the size of Earth to keep its geological engine running. So finding out that it's still warm and active inside is like discovering a sleeping giant is starting to stir. It forces us to ask a brand new question. What is powering this unexpected movement? This discovery wasn't made with a telescope looking at the surface. It was found by measuring gravity. NASA's missions have been mapping the moon's gravitational field with extreme precision. These measurements revealed tiny changes that could only be explained by something happening deep beneath the crust. The rock deep down is slowly flowing and shifting, a process we thought had stopped eons ago. It's a bit like watching a thick pot of honey slowly swirl. You can't see the motion easily, but its effects are there if you know how to look. This active interior is a total shock to planetary scientists who have spent their careers studying a supposedly dead moon. The idea of a geologically active moon upends decades of scientific models. We've built our understanding of how planets and moons form and evolve based on the idea that smaller bodies cool off quickly. The moon was our primary example of this process. Now that example is broken. This finding tells us there's a missing piece in our planetary science puzzle. Something is happening inside the moon that our theories didn't predict. It's a wonderful moment in science, a time when a new discovery makes us rethink the fundamentals. The quiet, predictable moon has just become one of the most exciting and mysterious places in the solar system again. So what is generating all this heat? If the moon is too small to have a molten core like Earth, where does the energy come from? The answer lies deep beneath the lunar surface, hidden in the rock itself. The secret ingredient is radioactive elements. Elements like uranium and thorium, which are unstable, have been slowly breaking down for billions of years. As they decay, they release a tiny amount of heat. Over a vast amount of time and concentrated in one area, this little bit of heat adds up. It acts like a slow-burning nuclear engine, keeping the moon's mantle warmer than it should be. This radioactive heating is not spread out evenly. NASA's gravity data suggests that these heat-producing elements are concentrated in a specific region of the moon. This creates a giant hotspot deep inside. This concentration of radioactive material is what has allowed the moon to stay geologically active for so long. It's an incredible idea. A hidden layer of special rock is acting like a buried power plant, keeping parts of the moon's interior soft and pliable. This is why the surface is still flexing and groaning after all this time. It's not the whole moon that's hot, but a very special, very important part of it. The surprising part is that this process is still happening today, on September 8th, 2025. After 4.5 billion years, you would expect most of this radioactive fuel to be used up. But there was apparently enough of it packed into one area to keep things warm. This is a major rewrite of the moon's life story. Instead of a world that died out quickly, the moon has had a long, slow-burning internal life. This radioactive blanket has kept it from freezing completely solid. It challenges our assumptions about how long planetary bodies can retain their initial heat and stay active, especially smaller ones that we wrote off as geologically uninteresting. This discovery has huge implications for our understanding of planetary formation. Why would all these radioactive elements end up in one place? It suggests that the process that formed the moon was much more complex and messy than we previously imagined. When a giant object smashed into the early Earth to create the moon, the debris didn't just mix together evenly. Instead, it seems some materials clumped together in specific ways. This radioactive hotspot is a fossil from that violent birth, a clue that tells us the story of planetary creation is far from simple and has long-lasting consequences for a world's evolution. Anyone who has looked at maps of the moon knows it has two very different sides. There's the near side, the face that always looks toward Earth. It's covered in large dark plains called Maria. These are ancient lava flows that give us the man in the moon. Then there's the far side, which we never see from Earth. It looks completely different. It is rugged, heavily cratered, and has almost none of those dark lava plains. For decades, scientists have wondered why the two sides are so drastically unalike. It's been one of the biggest mysteries in lunar science. Why would one world have two completely different faces? This new discovery about the radioactive elements provides a powerful explanation. It turns out that the hidden layer of heat-producing rock is located almost entirely beneath the moon's near side. This makes perfect sense. That extra heat from radioactive decay would have made the rock on the near side hotter, softer, and more prone to melting. This allowed magma to well up from the mantle and flood the surface, creating the vast, smooth Maria we see today. The near side had a geological advantage, an internal furnace that the far side lacked, which dramatically changed its appearance over billions of years. Meanwhile, the far side was left out in the cold. Without that extra radioactive heat, its crust became thicker and more solid much earlier. When asteroids and comets impacted the far side, the crust was too rigid for magma to push through to the surface. So instead of vast lava flows, the far side just collected more and more craters, becoming the battered landscape we see in our satellite images. The moon's two-faced nature isn't a coincidence. It's a direct result of an uneven distribution of elements deep within its interior. It's a story of the haves and the have-nots, written in rock and lava. This finding was made possible by incredible new technology. Missions like NASA's GRAIL, or Gravity Recovery and Interior Laboratory, orbited the moon and measured its gravity field with unprecedented detail. By tracking the tiny pushes and pulls on the two spacecraft as they flew over the lunar surface, scientists could create a map of what's underneath. Denser areas pull a little harder, while less dense areas pull a little weaker. This gravity map was our X-ray, allowing us to see through the rock and locate the hidden structures deep inside the moon, finally solving the long-standing mystery of its two faces. These discoveries are not just cool facts for a textbook. They change how we think about exploring the moon. Knowing that the moon is still geologically active has huge implications for future missions, like NASA's Artemis program. We now know there are regions with higher heat flow coming from the interior. These areas could be scientifically rich targets for landers and rovers. They might even be places where we could find resources or unique geological formations. We are no longer planning missions to a dead rock. We are planning missions to a dynamic world with a secret, simmering life of its own. Understanding the moon's complex interior also helps us understand other planets and moons in our solar system and beyond. The moon is our closest laboratory for studying planetary evolution. If a small body like our moon can stay warm and active for so long because of a concentration of radioactive elements, could the same be true for other worlds? Perhaps some of the moons of Jupiter and Saturn, or even distant dwarf planets like Pluto, have similar hidden engines that make them more active than we assume. The moon is teaching us a new rule for how planets work, expanding the possibilities for finding active worlds elsewhere. This new knowledge forces us to reconsider the timeline of planetary formation. The old models were too simple. The story of the moon's creation and evolution is more chaotic and interesting than we ever gave it credit for. This messy process, with materials not mixing evenly, might be the norm for how rocky worlds are built. Every new piece of data from the moon helps us refine our theories about how Earth itself formed and how rocky exoplanets orbiting other stars might have evolved. Our cosmic backyard is providing the clues we need to understand the universe at large. So, as we prepare to send humans back to the moon, we go with new eyes and new questions. The moon is no longer a finished story. It is a world that still holds deep secrets. What other surprises are waiting for us beneath the dust? Could this internal heat create conditions for unexpected chemistry deep underground? Could there be pockets of trapped water ice that we haven't found yet? The moon, our familiar celestial partner, has just reminded us that there is always more to discover. The more we look, the more we realize how little we truly know. What other secrets is it hiding?